Assalamu alaikum. Dear learners, in the previous lecture, I talked about various types of instruments and static characteristics those instruments can exhibit. Before starting the discussion of static characteristics, I discussed that there are two major types of characteristics that any instrument or a system can exhibit. The first one was the static characteristics, which we discussed in the previous lecture, whereas the other one is dynamic characteristics. In this lecture, I am going to discuss dynamic characteristics, which are the ones which an instrument exhibit during the time the measured value changes and the final output is reached. Later on in this lecture, I am also going to discuss various error sources and types of errors that can be induced or that can hinder the process of data collection from the instruments. Additionally, I'll talk about that how we can mitigate those errors and how we can solve the problem. Therefore, let's go. So I've already said behavior between the time a measured quantity changes value and the time when the instrument output attains a steady state value is called the dynamic response. And the dynamic response of any linear time invariant system can be represented through this equation. This equation is a very elaborate one. For example, the terms on the right side of the equation, they exhibit the inputs and the previous inputs, whereas the terms on the left side exhibits the output and the previous outputs. Simply stated, this equation tells us that the output of any system, which is Q naught, depends not only on the current input, that is Qi, but also on previous inputs and previous outputs. Over here, the delta terms or the differentiated terms, that is differentiation of Q naught with respect to time and differentiation of Qi with respect to time, these terms indicate previous inputs and previous outputs. For example, whatever you are today, you are not because of the current input or the current state, but because of all the inputs and all the experiences which you had after your birth till now. So each and every input shaped your personality, and whatever you are today is because of that input, and additionally because of the outputs as well. Because your experience is made up of not only inputs from the environment, but also how you reacted to them or what was your output to those inputs. For example, if I talk about a very specific case of a certain quiz, then the marks in your quiz are because of what experience you gained, how you learned for the quiz, how you prepared for it, and what you did before the quiz, and how you performed in some previous evaluation. So all these things are going to get together and make the output of the current quiz. So coming back to the instrumentation part, this equation looks quite scary, but it can easily be trimmed down. Therefore, we are going to use a knocked down version of this equation that will look much more easier to understand in our case. So the huge and scary equation which we saw in the previous slide can be reduced to a very simple one. For example, if we consider zero order system. For zero order system, the equation with which we will be left with will be this one. This equation states that as soon as an input is applied, the output is equal to some constant multiplied with that input, and that's it. There is no role of the previous inputs or the previous outputs. Now you must be wondering that what kind of a system can have this kind of a response. All the systems that exhibit this kind of a response are called zero order systems. And for zero order system, the output immediately moves towards the final value. That is, they have a minimum dynamic response. A very good example which you have already used is of a potentiometer. A potentiometer is a variable resistor whose resistance immediately changes as soon as you rotate the knob or adjust the slider on the potentiometer. It doesn't take it some time or even any time to adjust or to change its resistance. Therefore, as soon as you apply the input, the output changes. As soon as you rotate the knob, the resistance changes. These graphs also exhibit the same thing, that as soon as the input is changed or the measured quantity that we are trying to measure changes, the instrument's output also changes. There is no lag between the change in the input and the change in the output. Now coming towards first order systems or instruments, these kind of instruments behave in a bit different way than the zero order systems. For these systems, the output is dependent on the current input and the previous output as well. So if we can reduce the equation to the first order case, then we will be left with this thing. And we can easily simplify this equation into this form. In the numerator, the term is called sensitivity because it will dictate the gradient of the output versus input graph. And the value of tau is the time constant. This time constant is directly related to the time the system takes to reach the final output. So the first order instrument will have an output like this. As soon as the measured quantity or the input changes, the output starts changing slowly. The time constant is the time that output takes to reach the 63% value of the final value. Depending on the time constant, this output curve can be faster or slower to rise. Now you must be wondering that what kind of instruments do exhibit first order behavior? Well, there are many around you. For example, liquid in glass thermometer. As soon as you place this thermometer into your mouth or into some elevated temperature, the measured value has changed. So as the input changed abruptly, but you know that the output of the mercury in glass thermometer doesn't change that fastly. So it starts moving as soon as you place the thermometer into the new environment, but it will reach the final output after some time. Normally, thermometers used in your house has a time constant of 30 to 50 seconds. Another example of first order system is the fan in your room. As soon as you switch on the fan, the input to the fan, that is the electrical voltage, it abruptly changes from 0 to approximately 200 volts. But the output of the fan starts changing slowly. That is, it starts rotating slowly. It will take some time to reach the final speed or the final steady state value. You can find many other examples of first order systems around you. So over here, I would like you to find an example around you that you have seen and write it down in the comment section. As the output of the first order system is not achieved as soon as the input changes, the time taken by the output to reach the final steady state value should be considered and should be taken into account while designing the control system. Because the control system must know that the output of the system will not change promptly. It will take some time before it reaches the final steady state value. Coming towards the second order system, the equation will start getting a bit more complex. So now we are not just using the previous output, but previous to previous output is being used as well to calculate the current output. So the equation can be simplified and then rearranged into this form, where each constant over here has a specific meaning. Explanation of these constants will be out of scope of this lecture, so I'm going to skip the explanation and move towards this graph. This line signifies the measured quantity. You can see that the measured quantity changes at time t, whereas different outputs are shown for different values of zeta, where zeta is the damping ratio. This signifies how much output will be damped. In the figure, you can easily see that when zeta is 0, that is, for this output, there is no damping. So as soon as the input changes, the output starts changing, but it will never reach the final value and will keep on oscillating about the final value. Whereas for different value of zeta, if the input is increased, the response will now be shown by this curve. Over here, the output starts oscillating about the final value and reaches the steady state value after some time. And as you keep on increasing the zeta, that is the damping ratio, the output's oscillation will keep on dying and you will come more and more closer to first order systems. But if you increase the zeta beyond 1 or beyond a certain point, the system will become sluggish, even as compared to first order system. So, can you name any second order system which you have encountered during your engineering or anywhere in your life? These are the systems that will oscillate about the final value before settling down to it. I can name a few, for example, an accelerometer. And accelerometer is an excellent example of a second order system because as soon as you provide some acceleration to it, the output will start changing, but it will oscillate about the final value for some time before settling down. Another example is of a simple spring. If you stretch it and then leave it, what will happen to it? It will keep on oscillating about its final value and will settle down after some time. The amount of oscillations and the time it will take for settling down depends on the physical characteristics of the spring. Another example where second order system is desired or where these oscillations are desired is of a fighter jet. For example, if a fighter jet is flying and the pilot sees that there is some guided missile coming after the fighter jet, the pilot will try to change the direction of the fighter jet as soon as possible. So if the fighter jet was a first order system, then the pilot will provide the input to change the direction. The direction would have started changing slowly and ultimately it will set in a new direction. But unfortunately, during this time, the guided missile might have hit the fighter jet. So, a second order system will abruptly change the direction of the motion, but it will induce some oscillations into it. So over here, the prime concern is the abrupt changing of the direction. Therefore, a fighter jet is primarily a second order system. As soon as the pilot applies input to change the direction, the fighter jet abruptly moves towards the new steady state value or the new direction. And because of the abrupt change, the fighter jet is going to go beyond the final steady state value and then will come back and go below the steady state value and will keep on oscillating about the new steady state value for some time before coming to rest. In practice, damping ratio of 0.707 is aimed. However, in practice, inputs are rarely step inputs. Normally, they are ramp inputs. So, a damping ratio of 0.707 might not guarantee ideal response. Therefore, it is aimed that the damping ratio should lie between 0.6 and 0.8. This was everything about dynamic response. There are real-life systems that are exhibiting more than the second order systems. Additionally, this is everything about static and dynamic characteristics of any instrument or a measurement system. I hope you have understood the basic differences and the basic definitions of various static and dynamic characteristics. So, with this, I would bid you guys goodbye and take care.